Okay, the title of this tutorial is Mesoscopic Methods with LAMPS. So, we describe the mesoscopic methods for solving molecular dynamics. LAMPS provides some methods such as Langevin Dynamics, Brownian Dynamics, dissipative particle dynamics, lattice-Boltzmann, and stochastic rotational dynamics. So, soft macromolecules are immersed in small particles. And we have the Brownian motion for the macromolecular particles. Another important phenomenon is the solvent quality, which is affected by temperature. This affects also the macromolecular conformations. It's important description of the solution for the solvation for charged solvent solid systems. We also studied the molecular self-assembly process, where small molecules ensemble all together to form more complex molecules. This is true for particles such as micelles, vesicles, copolymers, gel networks. Another important factor is the hydrodynamic interactions, which are long-range interactions that are produced by the molecular motion of the molecules in the solvent. These affect the transfer phenomena such as diffusion, heat flow, and thermal diffusion, etc. There are different levels of approximation for describing the solvent particles. We have atomistic models. We have coarse-grained models. For atomistic models, full atomic description is provided, so bonded and non-bonded interaction are modeled. As a consequence, we have physico-chemical features described in good agreement with experimental results. We call precise structural, thermodynamic, and transport properties. For this atomistic model, we solve the Newton equation for the atoms. This is computationally expensive in terms of computing time and memory. So we can reach length and time scales of the order of nanometers and nanoseconds. However, because of the complexity of the atomistic architectures of the molecules, we can only reach some few millions of atoms in our simulations. The next level of simulation is the coarse-grained level. So coarse-grained models are formed by few real atoms that are replaced by defective particles. So these defective particles give us a qualitative description of the structural thermodynamic properties, and the transport properties for long-time scales in detail is provided. For this, the Newton equation are solved in the case of effective atoms. This is computationally cheaper than the case for atomistic models. So the length time scales are of the order of from 10 to 100 nanometers and from 10 to 100 nanoseconds. However, a mapping process is needed, so we need to map from the atomistic real systems to the coarse-grained models. This is called the coarse-graining process. Next, we have the mesoscopic level. So the mesoscopic models are introduced by replacing atoms and coarse-grained atoms by particle populations, and particle probability distribution are used instead of real atoms. Therefore, we can simulate a larger number of atoms and we can reach longer time scales. Because of that, we can describe properties such as the density and transport coefficients. We can say that the mesoscopic physical description is suitable for the hydrodynamic of the fluids. In this case, the Newton equations are not used, but Newton modified equations and another kind of kinetic equation such as the Boltzmann equation. These are cheaper in terms of computing time and memory. However, all atomic interactions details are neglected. For this, the length and time scales are different, so we can simulate systems in the scale from 100 nanometers to 10 micrometers, and times from 100 nanoseconds to 100 milliseconds. So, in the mesoscopic level, we study fluid particles that are in the regime between the atomistic and the continuum. So we have a description that is in between of these two regimes. Basically, the word meson means in Greek in between. As a consequence, we can use some techniques borrowed from the molecular dynamic simulation, and we can use some hydrodynamic techniques borrowed from the fluid dynamics. Therefore, we can describe the motion of macromolecules in liquid. Because of this approach, the thermodynamics and the hydrodynamics of these systems are relevant for a complete description of the fluid. As we said, the liquid and the fluids are described by using particle populations or probability distributions of the particles. So because of these factors, we can say that this problem is multi-scale. There are different scales of length and time. There is therefore a scale separation between solute and solvent particle motion. This separation is of several orders of magnitude. For example, we have water with a diameter of 0.27 nanometers and a colloidal particle of 100 nanometers. Relaxation times for these systems are of the order of 1 femtosecond for the case of the water molecule and 1 nanosecond for the case of the colloidal particle. Due to this scale separation, we can integrate out the solvent degrees of freedom, so the solvent and solute collision interactions are replaced by effective forces or random forces. In this case, we can employ stochastic models or kinetic equations for the description of these coarse-grained fluids. So it's very relevant for the mesoscopic system, the Brownian motion. So the Brownian motion is described by using the Langevin equation. The Langevin equation is the same as the Newton equation, but we have two new terms. In this case, we have the friction coefficient. This is the friction force due to the viscous medium, and this is the random force produced by the constant bombardment of the solvent molecules. So certain colloidal particle, for example, moves according to the Newton equation, that is included by considering this external force. So this force considers the potential forces derived from conservative potentials and from hydrodynamic fields, and there we include a friction term given by the Stokes law, and stochastic force, which is modeled by using a stochastic process which introduces white noise. In this stochastic process, the force averages to 0 in time, and the variance of the force is different to 0. In fact, this variance relates the fluctuation of the forces to the dissipation in the system. So the dissipation of the system is described by considering the temperature and the friction coefficient of the medium. The Langevin equation is capable to describe particle diffusion. We can calculate the diffusion coefficient from this approach. Another way to describe the mesoscopic systems is through the kinetic theory. So we use a Boltzmann equation to describe the fluid and gases or liquid systems. In this approximation, we employ a probability distribution function where f is the probability distribution function of a particle at certain position r with velocity v and at certain time t. The evolution of this probability distribution function is described by the Boltzmann equation. So this Boltzmann equation describing the transport equation for the probability distribution function, where this c term is the collision operator. So the time evolution of this probability distribution function is coupled with the collisions through the collision operator. There are several analytical methods for solving this Boltzmann equation, but it is possible to find a stationary solution at equilibrium. The particle velocity distribution at equilibrium is the Maxwell-Boltzmann distribution. So this is the Maxwell-Boltzmann distribution, the very well-known Gaussian expression, where this is the probability of having a particle with velocity v, a certain temperature T. So the fact of obtaining an equilibrium distribution function from the Boltzmann equation, it is known due to the H theorem. So the H theorem establishes that the equilibrium solution for the Boltzmann equation is the Maxwell-Boltzmann distribution. So one of the properties of the Boltzmann equation is the Galilean invariance. So there's certain reversibility in T in the Boltzmann equation. It is possible to establish an equation of a state for mesoscopic fluids. So if we want to establish an equation of state, it is necessary a more formal treatment by using statistical mechanics methods. Right. Now another important factor in the mesoscopic systems of fluids is the hydrodynamic interactions. The hydrodynamic interactions are long-range interactions produced by macromolecular motion. See, this macromolecular motion occurs in the liquid. The hydrodynamic interactions are coupled with Brownian motion and with the fluctuation dissipation theorem. As a consequence, it can be described by using the Hermack-McCammon equation. So this is the position of the particle, and this equation considers the coupling with the fluid and the coupling of the diffusion of the particles with the force. Here we have the stochastic force, where the tensor D and V are related through the fluctuation dissipation theorem. For modeling the tensor of diffusion, it is possible to use the Ocean tensor, which goes as 1 over r, therefore is a long-range interaction. There are another approximation for non-point particles, such as the Rodney-Prager-Yamakawa approximation. However, it is hard to solve this equation in complex geometries. This is very frequent in the study of soft matter in confinement. The main idea of the hydrodynamic interaction is the transferring of linear and angular momentum, and this occurs through the collisions between the solvent and the macromolecular particles. This collision between the mesoscopic particles and the macromolecules can be described by using different algorithms. The main idea of modeling the hydrodynamic interactions between macromolecules and solvent particles is through the lattice methods. So we can model the transferring of energy and momentum using discrete systems. So we discuss now the mesoscopic hydrodynamic properties. We can describe a hydrodynamic system by using dimensionless numbers. In this table, we present different dimensionless numbers. We have the Schmidt number, the Mach number, the Reynolds number, the Nansen number, and the Peclet number. The Schmidt number describes the relation between the viscous effects and the diffusion effects of the solvent. So this determines whether we are modeling a liquid or a gas. The Mach number is the ratio between the characteristic velocity of the system and the velocity of the sound. The Reynolds number is the ratio between the inertial forces and the viscous forces. So it's given by U, that is the system velocity, L, that is the system length, and U, that is the kinetic viscosity. This number is related to the turbulence phenomenon. Then we have the Nansen number, that is the ratio between the framing path and the system length. Finally, we have the Peclet number, that is the ratio between the advection force and the diffusion or the Brownian motion. For example, if the hydrodynamic interactions are to be relevant, this only happens for Reynolds smaller than 1. And for simulating a liquid, we have a Schmidt number larger than 1. Finally, for having a Brownian motion behavior for the solute particles, the Peclet number is smaller than 1. Because this is a multi-scale problem, there are several relaxation times in this system. We have the first scale described by the acoustic or ballistic relaxation time, and then it goes the kinetic, that is related to the viscous effects. Then we have the diffusive relaxation time that describes diffusion of the particles. And finally, we have the Stokes relaxation time that is related to advection or the transport of the particles. All these numbers are linked together and related through the dimensionless numbers according to these formulas. Okay, so there are several mesoscopic simulation methods. We have Lagrange methods and Euler methods. In the Lagrange methods, the system of reference moves with the particle, whereas for Euler methods the system of reference is fixed. There are several Lagrange simulation methods. So we have Langevin Dynamics and Brownian Dynamics. We also have dissipative particle dynamics, that is DPD here, and the stochastic rotational dynamics, SRD. For the Euler simulation method, we have the lattice-Boltzmann and the smooth particle dynamics. Both methods are discrete and employs for the description of the fluid a mesh. So about the mesoscopic simulation methods, the equations of motion are not described by the Newton equation. Therefore, the integration algorithms and the boundary condition employ different techniques. All mesoscopic simulation methods fulfill the H theorem, the Galilean invariance, and the dissipation fluctuation theorem. It is also possible to derive Green-Kubo transport equation for all methods. Here, there are some examples of the equation of motion. For example, for the DPD Langevin modified equation, we have the same equation for the Langevin equation that includes conservative forces and random forces, but including a dissipative force, we include the hydrodynamic interaction directly. That's why sometimes DPD is called as a modified Langevin equation. Then we have the stochastic rotational dynamics, where a stochastic rotation of relative velocities is implemented to simulate the collisions. So the particles are placed in a lattice or in a mesh. So for simulating the collisions of the particles, we move the velocities of the particles by using a linear operator. So the position of the particle is updated by changing this the velocity of the particles by changing this term that emulates the collision between particles. Then we have for the lattice-Boltzmann a probability distribution function. The lattice-Boltzmann is a discrete version of the Boltzmann equation. So to describe the probability distribution function, it is required a collision operator that is simplified in this discrete version, where FQ is just the external force, or it could be the stochastic force. Right. So there are scopic packages in LAMPS. So LAMPS provide with mesoscopic methods such as Langevin, Brownian dynamics, dissipative particle dynamics, and stochastic rotational dynamics. It is also provided the lattice-Boltzmann method. The Langevin and Brownian dynamics are implemented directly by compiling all the main packages. However, for dissipative particle dynamics, stochastic rotational dynamics, and lattice-Boltzmann, it is necessary to compile different packages. For example, for the dissipative particle dynamics, it is necessary the package user meso. For the stochastic rotational dynamics, it is necessary to compile the SRT package, and for the lattice-Boltzmann, the user LV package. So the installation of these packages is very simple. So in the source directory of your LAMPS installation, you only have to make the packages by using the syntaxis yes and the name of the package. For example, make yes SRD, make yes user DPD, and make yes user LB. After that, you have to compile the executable file. In this case, we use the MPI executable file. Right. So in the next tutorial, we'll be discussing the Langevin Dynamics technique. So in here we are describing the main physical properties of this package and some simple examples. For now, I thank you your attention and see you next time.